This is a omnidirectional horizontally polarized antenna for the 70 centimeter band, sometimes referred to as a cloverleaf antenna or a big wheel antenna. First got interested in this antenna when I was asked to construct a antenna for the VK6 RTU beacon in Kalgoorlie. So I was asked to construct two antennas, one for 6 meters, one for 70 centimeters. The 70 centimeter antenna, after a bit of research on the internet, I found this paper where they were studying various configurations of cloverleaf or big wheel antennas for the optimum omnidirectional horizontally polarized antenna configuration. The paper's kind of interesting. The conclusion reached was that a 5-petal big wheel antenna was the most ideal configuration. So it produced the most uniform omnidirectional radiation pattern, and it was fairly broadband. So that's what I constructed. My version is a little different in that I was trying to get the SWR down, so we manipulated the petals slightly, but other than that it's essentially the same antenna. So what was satisfying with the results was that it came up very close to the results in the study in the paper, in that the gain is essentially neutral compared to a dipole, very uniform pattern. It's quite broadband, probably from about 420 megahertz or 425 megahertz through to about 460. So it's unusually broadband. The antenna was constructed and installed at the beacon site. After the installation, we drove out of Kalgoorlie. It's kind of not a very scientific study, but as we were switching between the various beacon frequencies, 62 and 70, what was interesting was the last beacon frequency we lost on the departure was the 70 centimeter, which is kind of not what you'd expect. Again, not the most scientific study, but it did indicate the antenna was working well. So always had the desire to circle back and have a look at this antenna again. So I have, and this is the result. I am going to do some more detailed measurements this time, and I'm also going to try and see what its performance is like for satellite work. It's potentially not ideal for satellites, but you know, you've got to try these things. So we're going to push into now the construction, testing and installation of the antenna. On the bench is one of the 5 active elements cut to length, ready for bending. The total length is 690 millimeters for the 435 megahertz band. This is the bending jig for forming the elements. There's a few steps in this process. This is the first, I guess, after cutting. So, as per the drawing, this is set up from the 0 point, and the element is set 6 millimeters back from the 0 point, so that's how it's set up on the jig. And then it will need to be locked in place. bit of subtle hand massaging to form the shape, just checking against the jig. I don't get too excited and overbend anything. Right, the element needs to have a twist placed in it to get the correct attachment points, for want of a better word. So we're going to do a rotation twist from the 60mm from the end mark to the 110mm. So that will just rotate over that section, and on the other side there will be a twist between 60mm from the end and 110, and this one will then be rotated at a angle for mounting. Okay, so simply we've got a shifter or adjustable wrench, and it is simply twisted to get the correct angle. So at the end of the day, we should end up with something looking like this. So at the 110mm point, we start our roll, twist, and stops at 60mm. 110mm, start our roll, stops at 60, and then we do our angle bend. And when everything's clean and polished up, we should have a nice clean element like this. Right, this is the central mounting hub per the drawing. This is for the bottom sections of the elements to attach. 100mm in diameter, 3mm holes for pop riveting the elements on. The central hole is just over 16, almost 16.5mm. Almost exactly 16.5mm. This has been deliberately made so that it's a tight fit for the end connector retaining nut. So the idea is it's going to be mounted in this fashion, and that will screw in tightly. Now, I got the precise hole diameter by using a step drill, and at the last point we didn't go all the way through, we just beveled it in either side until we got the size that was going to be a tight fit, so that the nut will literally cut a thread into the aluminium plate. So the idea is that we're going to mount the end connector body to the plate. So just, like I say, we've cut what is close to a thread till it gets to the end, and it will flop around. It gets to the end of the nut thread, and then the end connector body screws on. Once that's tightened up, it is really tight and solid, and this is the 6mm stainless steel stud. It's had a copper sleeve crimped on quite tightly, and then soldered to a center pin for the end connector. So this is how this goes together. goes the end connector retaining washer. So this varies a little bit from end connector to end connector type, and it's simply slid into there, and then we're going to put some epoxy resin to hold that in place. Two-part epoxy resin. This is the completed assembly of the main hub for connecting the elements. So the epoxy glue is set, it's quite strong, pins nicely centered. We've also got a rubber grommet that was sort of modified and fashioned so that it would fit snugly in there. It's also got a bit of epoxy glue around it as well. So that should be completely watertight and secure. So the next part of the process is to attach the elements to the hub. Now we're doing aluminium to aluminium jointing. Aluminium's known for oxidization, so at the point of contact, give the aluminium a nice clean. We're using some steel wool here. Get all the oxidization off the aluminium. Give it a bit of a general clean, I guess, for appearances. But the main point, of course, is the point of contact. And the element is the same, so this is the attachment side, so we'll give that a nice clean. Pop rivet some grease, or in this case some aluminium jointing compound. We'll just smear a tiny bit on here. Don't want to make a mess. rivet. Again, we'll just put a small amount of jointing compound on there, pop rivet in, nice and snug. Right, the other end of the elements will attach to this disc. Again, aluminium needs to be cleaned back and just do clean all the elements. Hopefully this will go nice and smoothly. Okay, the stainless steel stud, it's actually quite long. It will be trimmed off once everything is assembled. So the first thing we do is just a spacing nut, make that reasonably high. Washer on there. The disc also, again, needs to be cleaned of any oxide, make it nice and shiny. With the antenna on the test stand and connected to the nano VNA, we're measuring the SWR, or the matching of the antenna, between 430 and 445 megahertz. The nano VNA has been calibrated to the point of attachment for the antenna, so we're actually looking at the antenna proper, and we're getting exceptionally good results given the target frequency was 438 megahertz, getting an SWR result of about 1.33 to 1, exceptionally good over the target frequency. And from 430 we can grab that. To 445, less than 1.6 to 1, exceptionally good. Down this end we've got almost 2 to 1, but still exceptionally good result for that kind of broadband. We'll just take it out a bit and have a look at how broadband this antenna is, because it does appear to be exceptionally broadband. So we'll do a start frequency of 400 megahertz and stop 550 megahertz. Maybe we'll call that 500. Stop. So from 495 odd megahertz, we've got less than 3 to 1 SWR, all the way down to just over 400 megahertz. So quite unbelievably broadband. But the target frequency of 438 megahertz seems to be where we get our best results, so that's very satisfying. Interestingly, the paper on the antenna of a similar design noted that getting a low SWR, or a good match for the antenna, was a real issue, and they noted that the antenna was quite inductive and believed that adding capacitance would be a way of getting a better match. So the construction of this antenna, which involves two discs, a large disc for attaching the elements to and a smaller disc for the active end of the elements, does look a lot like a capacitor, and it does have the added feature of if you loosen off the retaining nuts, that the distance between the two discs can be adjusted and has a direct effect on the SWR, or matching. So I've made those adjustments, and this is the best match I get. So I'm not sure that with this design we may have overcome the shortcoming of the design in the paper by adding the capacitance inadvertently. And also it's got the flexibility of adjustment. So that's the final result for the SWR, very satisfying. Okay, I'd like to have a look at the Smith chart now. So we're still in SWR mode, and we're sampling from 300 megahertz to 600. It's a little bit wide. We'll just bring that in first. We'll start around 400 megahertz. Stop at 550 megahertz. So we're still pretty wide. Display format.
Okay. So on the Smith chart, we're getting our best match on 438 megahertz roughly, but that's out here, so it's slightly inductive. And if I bring it down to where it crosses the center line between inductive and capacitive, which is indicating the resonant frequency, and it's at 459 megahertz, which is higher than I would have expected. It's also interestingly that the paper indicates similar results, and my previous construction of this antenna also produced the same results. It sort of indicates that the active petal elements could or should be a little bit larger, maybe as much as 5%. Just interesting. So if I was to take that back to the SWR, let's see, we've still got a pretty good SWR at that frequency, 1.7 to 1, but well above where we really want it to be. Where we want to be is around about here, about where we've got the best SWR figure. We'll just bring that in a bit tighter. So yeah, this is the range that we're really looking at, and we're showing to be somewhat inductive throughout. So yep, interesting. Food for thought. If we build another version of it, we might try and play around with making the petals a little bit larger, but despite that, it is matching up pretty well, and can't complain about that. Alright, on to the antenna gain measurements and range testing.
Some comments on the antenna range testing setup, or the antenna gain measurements. It is simply the antenna under test as compared to a standard dipole cut for the same frequency. The source antenna in this case is also the same type of dipole antenna. Not necessarily they be the same, but in this instance they are. The antenna source and reference and antenna under test are placed between 2 and 3 wavelengths apart. It is important that they're not much further than that, because ground reflections and multipathing will interfere with the results. So 3 wavelengths is a rough maximum. The antennas are set at least 2 wavelengths above the ground. So at 438 megahertz, that relates to a separation of about 2 meters and a height above ground of 1.5 meters. So that's physically what the setup looks like. The nano VNA is calibrated from the source to the reference dipole, and the display is zeroed so that we're getting a 0 dB return with that antenna. Then we change over the reference antenna to the antenna under test, and we measure any positive or negative gain, and that determines the gain of the antenna under test. So that's simply the arrangement. This is a backyard setup, so it's a little bit subject to some minor variations, but is essentially a good guideline to ascertain the performance of the antenna. So that's the setup, and we'll push on with the measurements. The antenna range test has been set up, so we've got a source antenna and a reference antenna, both of which are simple dipoles. So these will be used to set the baseline. So we're going to start at 430 megahertz, stop 5 megahertz. Calibrate, reset, calibrate through, done, save. The scale to 0.5 dB per increment, and because we could get a negative figure, we're just going to do the reference position. Alright, so let's put it in the center. So we've got 0 baseline, plus 0.5, plus 1, 1.5 to 2.5, minus 0.5, minus 1, minus 1.5, 2, and minus 2.5. So we're now going to swap out the reference antenna for the antenna under test. Alright, with the antenna under test in position, we're recording about gain neutral, somewhat to be expected, a little bit on the positive side, but it's an omnidirectional horizontally polarized antenna. Neutral gain at 438 megs. Right, the scale has been moved out to plus and minus 20 dB, and the test I want to do now is to examine cross polarization. So the source antenna will be rotated into the vertical position, and we'll see what cross polarization losses we get. Okay, we just let things settle down, and so the source dipole now is in the vertical position, and we're recording negative 17, almost 18 dB, which is what we would expect if we were cross-polarizing. If we weren't seeing that, then the antenna may not be performing the way we would hope it was. So that's the cross polarization figure at minus 17, almost minus 18 dB. That is the successful completion of the 5-petal cloverleaf antenna. Keen to hear comments below. For a bit of fun, I listened to the Russian RS-44 satellite beacon as it passes to the north over the Indian Ocean. It can be heard right down to the horizon. And thank you for watching.